There are several different types of standard analog signals that we use when we move data, numerical data, between programmable logic controllers and field devices. While there are PLC input cards that are designed to measure specific signals from specific field devices, such as RTDs, thermocouples, weight transmitters, it is more common for field devices to modify the signal that they transmit in order to be able to adhere to a standard. Let's take a look at some of those standardized signals. 0 to 10 volt DC signals have been around for a long time and they're used in many places. These signals are being replaced by other types as time goes on, but it's still very important to understand them since many of them are installed in various facilities. There are advantages to the simplicity of the 0 to 10 volt signal. You can measure the signal with minimal disruption, since voltage can be measured without disconnecting any wires. A simple circuit constructed of a potentiometer and some batteries or a power supply allows testing or calibration. 0 to 10 volt signals are wired in parallel with obvious polarity. But this signal wouldn't be going away if it weren't for having some disadvantages, so let's take a look at those. These signals require a minimum of 3 and typically 4 field conductors between the PLC enclosure and the field device. While it is possible in some circumstances to be able to use more than one input device on a single voltage signal, many voltage inputs interfere with one another. Perhaps the largest reason not to use a 0 to 10 volt signal is the impact that the nature of the signal has on calibration issues. Voltage drop across the conductors can change with ambient temperature, causing a calibration performed in the summer to drift in the winter or vice versa. And longer conductors drift more. We should also note that the PLC can't tell the difference between a zero signal and a lost signal. Current loops solve many of the problems of voltage signals, but require increased skill when it comes to wiring and troubleshooting. Because all points in a current loop have the same current, it is possible to add numerous devices in series in a loop and have all of them get the same signal. This also makes the current loop more robust for holding calibration during temperature changes and producing a more accurate signal across longer conductor lengths. Some current loop transmitters can detect when their signal is broken or when the signal cannot reach the milliamp output that it's intending to create. Like the 0 to 10 volt transducer, a 0 to 20 milliamp transmitter also requires a minimum of 3 and typically 4 field conductors. A typical multimeter requires breaking the circuit and adding the meter in series in order to measure current. This is also true in our 0 to 20 milliamp current loop, and it's always important to consider the process implications of breaking any signal in order to make a measurement. Like our 0 to 10 volt signal, it is impossible for the electronics to distinguish the difference between a zero signal and a broken conductor. Most people find current loops more challenging to wire correctly than a voltage signal, and a lot of this is due to polarity. So when you are looking at the polarity of a current loop connection, I recommend looking at the direction that the current travels through the device between the terminals, rather than trying to look at it from a perspective of which terminals are negatives and which terminals are positives. 4 to 20 milliamp loops are an improvement on the 0 to 20 milliamp current loop. Moving the zero signal from 0 milliamps to 4 milliamps enables both the PLC input and the transmitter to detect the difference between a zero signal and a broken signal. And while not every field device is designed to take advantage of it, it's possible to limit field conductors to only 2 through using the 4 milliamps at the bottom end of the signal in order to power the transmitter. 4 to 20 milliamp current loops are the clear winner among the standardized signals. However, that doesn't come without increased complexity that makes it more difficult to troubleshoot and more difficult to wire. Also, The differences between loop-powered and instrument-powered circuits must be understood. It is possible to measure a current loop on an input that is designed for voltage. This is typically accomplished by adding a 250 ohm resistor across the input terminals on the PLC input card or, for example, on a chart recorder. Understanding this technique can be a huge benefit when you have a dual input card that can receive both current and voltage signals on the same channel. If the current channel is damaged, you might be able to convert it to a voltage. We can use Ohm's law to determine what the voltage would be across the 250 ohm resistor based on the current inputs that we expect to create. So at 4 milliamps multiplied by 250 ohms, we get 1 volt. At 20 milliamps multiplied by 250 ohms, we get 5 volts. That produces a 1 to 5 volt signal that represents 0 to 100% of what we're measuring. Resistor choice is important. It needs to have both a very low temperature coefficient and very tight tolerances. While some degree of error in the tolerance can be calibrated for, temperature coefficient is a measurement of how the resistance changes as a function of ambient temperature. 250 ohms can be a significant factor in the resistance total of a current loop. Lower loop resistance leaves room to add more devices in the loop if necessary.